said that the mice ate more. They ate more calories, actually, even with the BCAA lowered. So how come they lost weight? Where did the extra energy go, or did they not absorb it?
So as far as we can tell, they did absorb it. What we measure via indirect calorimetry is that they are literally burning more fuel off. And so you could imagine that some of this could be related to activity, but it's not. So the mice move just as much no matter what type of diet they're eating. And they're literally burning up more energy in the form of heat. And so some of the things that we can see is that there's browning and beiging of white adipose tissue. So their white adipose tissue is becoming more metabolically active, actually gaining more mitochondria. That's what makes brown adipose tissue or beige adipose tissue brown, the additional mitochondria. Those mitochondria are quite active. What exactly how this is happening remains to be seen in some ways. Because we're still trying to figure out exactly what the physiological mechanisms there are that are leading to increased energy expenditure. But there's a lot of different changes that happen to the animals.
And this was when you started the diet kind of later in the mouse's life, right? And
we've done a couple different ways. Overall, protein restriction, in particular, we've done in both young and aged mice. And aged mice have a little bit of a blunted response to protein restriction, but broadly speaking, there are similar effects in both young and old mice.
Okay. One thing is, when humans get older, we tend to need more protein. Do mice have a similar kind of life trajectory?
The life trajectory is slightly different, but just like humans, mice do experience sarcopenia when they're older. And so one of the things that definitely is worth thinking about is what ages, how age would interact with diet. And so, you could well imagine based on humans that humans who are younger might benefit from the effects of protein restriction, whereas people who are older and at risk of sarcopenia might not, because that might stimulate additional lean mass loss. And so I think there's definitely a lot to be thought about there. And there's some epidemiological data that Morgan Levine had published back in 2014 as well, suggesting that some of the effects of dietary protein restriction on longevity are only seen in people who are under the age of 65. And so it remains to be seen what the best diet for each age is. There's also, quite a bit of variation between the sexes as well as between different strains of mice, suggesting that genetic background plays an important role in the response to dietary protein as well. And so I think longer term, one of the things that we hope to be able to do, but hopefully, the field overall will be able to do as well, is move towards a point where we can figure out on the basis of your age, maybe your microbiome, your genetic background, what the ideal diet would be. And so for some people, I think that's probably going to be a diet that's lower in protein, but you could certainly imagine that since different people respond to these diets in different ways, other people might benefit from some of the other, diets that people are following for health, be that the Mediterranean diet or the keto diet. So I think it remains to be seen, how we can figure out what the best diet for each person is.
Yes, I think that would be really interesting, that kind of personalized medicine. Originally, you did a trial where you gave the mice restricted BCAAs from being weaned, right? And then I think you saw a life extension in males, but not in females. So can you talk a little bit about what you saw in that, and why do we know why it's different between the two?
So overall, so you're completely right. So we restricted both progeroid mice that are sort of rapidly age, as well as wild type mice starting at weaning, and fed them either a low control diet, a low protein diet, or a low branched amino acid diet for the rest of their life. And the mice that were fed either low protein or low branched amino acid diet, if they were males, lived over 30% longer. So it was a pretty massive extension in terms of what we saw. And also the controls were long-lived to begin with. So, this was very impressive. And the, mice all the way out at the end of a curve were sort of similar length and longevity as compared to a lot of calorie restriction studies. Whereas females, actually, we didn't see that effect. And so overall, females seem to have no effect on longevity at the particular dose and timing of protein restriction that we chose. So it remains to be seen why that is. Certainly, in some studies that have been done in Drosophila, there seems to be sex-dependent differences as to how flies respond to differences in dietary protein. And so in Drosophila, it seems like males benefit the most from a low protein, high carb diet, whereas females might benefit more from a high protein, low carb diet. We don't know if that, plays out in people either. What we do know is that definitely there seems to be a sex effect there. In various other studies we've done with protein restriction, the direction of which sex benefits tends to vary based on genetic background. So there may be a role in that as well. And at the molecular level, we looked at these mice. The males actually had less frailty as they aged. So, we thought the muscle would be an interesting tissue to look at. And looking at transcriptional profiles from those tissues, we found that the effects of the diets on male and female muscle were completely different. So low branch amino acid diets have very different effect on males than females. And in fact, mTOR signaling was specifically deregulated or repressed in the muscle of the male mice that had a low branch amino acid diet, but not in the females. So at least there's a correlation there with the effects of the diets on mTOR activity.
I saw that. I was just surprised how lowering BCAAs could not impact mTOR. I mean, it just seems like it should, but it didn't in the females, right?
I mean, a couple of different things to think about. First, when you look at male and female mice, they tend to have different basal levels of mTOR activity in the first place. And that may be tissue dependent as well. So there's a lot of differences in the mice between male and female, just black 6 mice, as how mTOR activity changes as the animals age. Another question is, well, we're lowering branched amino acids, but how much branched amino acids does a mouse normally need? So maybe males probably have more muscle mass. Maybe they need more branched amino acids. Maybe that's why there's an effect on mTOR signaling. Females, they'll probably have less lean mass. So maybe, normally speaking, maybe they burn off a lot of their dietary branched amino acids and catabolize them into fatty acids and sugar. So there's a lot of different questions there that really remain to be addressed.
Start the mice off weaning them with low BCAA. Does that impact their growth? Because BCAAs are related to growth. So do you see any physiological differences in the mice who were restricted from like almost birth, I guess?
So the important point to note is that we actually did this because progeroid mice have a very short lifespan, right? So if you don't start interventions in progeroid mice at weaning, you are not going to see anything because they age very rapidly. And so that's why we actually had this, and we had the wild type controls at that age. We also tried this in mice that were midlife, and we saw benefits to metabolic health. We saw improved glucose tolerance. The mice were leaner. They didn't live longer. Although it's possible there were some effects on power there that remain to be seen. We did see some effects on cancer rates. So cancer seemed to be lower in older mice that were placed on a BCAA diet, more like the human equivalent of 40 or 50 years old. So there definitely seems to be positive, not negative effects of branched amino acid restriction in either of those ages. Certainly, if mice are young and growing for a lot of their lifespan, and so if you start restricting branched amino acids there, they gain lean mass and fat mass more slowly. Overall, the effect is usually concentrated on fat mass, so the mice are leaner as they get older, even though they have a lower amount of lean mass accretion. That's a little bit different from growth, because if we think about growth in a person, right, we might think about height. And so we didn't really look at length in the mice, but we didn't really notice an effect on that in any event.
Right. And so they're a little bit lighter. Do you understand why they're less frail? Because that does seem strange to me, that if you have less protein, you're less frail.
Yeah, we're starting to do some experiments now where we look more closely at the relationship between dietary protein levels, exercise, and what the effects on muscles are. Certainly there's a lot of contributions to frailty, but I think many of them are related to skeletal muscle function. And, skeletal muscle mass may or may not be as important as skeletal muscle quality, right? You might have a large muscle that's not very good versus a smaller muscle that is really healthy and athletic. And so that's something that remains to be seen, to look at muscle function and fiber type and so on as the animals age on different levels of dietary protein. We're also going to be trying some experiments where we sort of measure more directly the impacts of exercise.
Okay. And so these were all restricting all three of the BCAAs, not just isoleucine, these experiments we were talking about.
The longevity experiments that we published so far are all focused on all three branched amino acids. More recently, we've shown that isoleucine has this really potent effect on metabolic health in young mice, as well as in diet-induced obesity. And we're writing up now some studies where we're looking at isoleucine's effects on longevity as well. That regulates the response to dietary protein as well as isoleucine.